to my lecture on feature learning. My name is Alex Jung. I'm Assistant Professor for Machine Learning at the Department of Computer Science at Aalto University. And yeah, I really would like to encourage you to ask questions. Stop me anytime during my presentation, either by just asking a question via audio, or I will also try to regularly look up the chat, so you can also post questions there. Okay, so the learning goals for this lecture are to understand the challenges with long raw feature vectors. So I will talk about feature vectors in a second, and why we have a lot of features typically. Then I will explain the basic idea of feature learning. I will show how we can use feature learning to visualize data and also to protect privacy. The main technical part of my lecture is on one particular method for feature learning, which is called principal component analysis, which is maybe the most widely used and most basic method to learn features. Then I will also talk about random projection as an alternative method for learning features. Okay, so as understood, you had already some lectures on concepts in machine learning. I want just to start with a quick refresher on the components of machine learning. So in machine learning methods, you typically combine three components. So the first component is data. Data in the sense of having a lot of data points. Data point is a highly abstract concept. So a data point can be a person, a data point can be a pixel in an image, a data point can be an image. So the important thing is we have many of data points. And data points are characterized by features, which is what we can measure or determine easily technologically. There might be features that we could, from a technological point of view, access easily, but we cannot because of privacy constraints. And then there are other aspects of data points, which are labels, which is this higher level information we're interested in. For example, the label of a data point representing a patient might be, does this patient need intensive care unit within the next week? And we would like to predict this label based on the features. And in order to predict this label, we use a predictor function. So this is a functions from the features to the labels. Like in linear regression, we use linear functions. In deep learning, we use artificial neural networks to represent these functions from features to labels. And we learn, so machine learning is about learning a function or a predictor map, which are represented here by these curves. So you see here 4 different predictor functions, and these predictor functions are all from some set of predictor functions, which we call hypothesis space. We typically cannot allow any possible predictor function. There are simply too many of those. So we restrict ourselves to a subset of predictor functions like linear functions or decision trees or artificial neural networks, which is called deep learning. So this is just refers to different choices for classes of predictor functions. And let's say we have here 4 different predictor functions. And what machine learning is about, well, you try to find or to identify those predictor functions which best fits the data. And the fit of the data points needs to be quantified, and for this we need loss functions. There are different choices for loss functions, like the squared error loss or the logistic loss, or other loss functions used for classification problems. And machine learning is essentially an optimization problem, the optimization of the predictor function to minimize the average loss. So are there any questions up to this point? Okay, so which predictor function would you prefer? So which of these predictor functions would you prefer here? Do you have an intuition? What is the best predictor function? Which one should we use? What about this predictor 4? This predictor 4 perfectly fits all training data points. So we have 4 data points for which we know the label and the features, and we have here one predictor which perfectly fits all these data points. Is this for sure the best? Is this always the best choice, or how do you feel about this? Should we use predictor 4 here?
I think no, because that's a typical overfitting of the training data.
Okay, yes, very good point. So when we have a lot of features, even linear predictors can represent highly complicated functions. So if you have a lot of features, you will almost for sure get zero training error. So you will find one linear predictor, although it doesn't look linear here, but in a higher dimensional space, you find such linear predictors which perfectly fit the training data. So having a zero training error is just a first step. So it just tells you that you were able to optimize your predictor. So you know how to optimize predictor functions. But statistically, regarding how well does the predictor on a new data point, for example here, it doesn't tell us much. So it just says we have found one predictor function which perfectly fits the training data. And this overfitting, as I said, happens quite easily if we have a lot of features. So, and this is the standard case, so to say. Nowadays, in our technology-driven society, we collect a lot of features about individuals. So consider the problem of predicting the risk that a certain person or patient needs an intensive care unit within the next week. So this is important because these predictions allow, for example, ministers for healthcare to decide, do we have enough resources? Do we have enough beds, intensive care beds in our hospitals? Or should we need more? Should we prepare more? In order to predict the need of an ICU, we can use the features of a patient. So is he currently or she ill? What are the current health parameters, previous diseases, so all the health records. We can also use mobile phone data. Did this person just come back from a ski resort in Austria or from Italy? So we might identify this using the mobile phone data, or we might not even need the mobile phone data. We just look at the social media posts, because if the person posted a snapshot from the ski trip in Ischgl in Tyrol, okay, then we might suspect that this person was exposed to, for example, coronavirus cases. So these are all features, and we have tons of features. So we can stack all this data into a long feature vector of length n, and this might have tens of thousands, millions of features for each individual person, for each data point. So we will typically overfit the training data. So does any one of you know roughly how much training data do we need if we use linear predictors with, let's say, 10,000 features? So you will overfit the training data as long as you have less than as long as you have a smaller number of training examples than the number of features. So if you have, for example, here 1 million features, which is not unusual nowadays because we collect so much data about individuals that we can easily find 1 million parameters, quantities that characterize the person. So if we use 1 million features, we need at least 1 million data points unless we overfit, otherwise we overfit for sure. So you will typically overfit when you have a lot of features. And this should motivate to try to reduce the number of features. So one problem with long feature vectors, and this is the standard case nowadays, in many applications we collect a lot of data about individuals and we have a lot of features. So using these raw features would put a pressure on having a lot of training examples. Another example could be image processing, where one data point is not the patient, but one data point could be an image. And we could stack the pixels of an image into a feature vector. So each feature corresponds to one pixel and the red, green, blue values. How many features do we have for a typical image that you can take with your smartphone? How many pixels does such a snapshot have? Any guesses? Does anyone have a smartphone with a camera? So how many pixels does your camera have on your smartphone? 1,000? 100 pixels? 10 megapixels I have read here. So 10 megapixels, which means 10 million features. So one single snapshot that you take with your smartphone, if you would stack it naively into a feature vector, gives us a feature vector of length 10 million. And if you want to do something, for example, classify images if they show a cat or no cat, this would mean you need 10 million labeled images for which you know if there's a cat or no cat on the image. So you typically don't want to work with long feature vectors. You typically want to have short feature vectors which contain only very few features which are highly informative and relevant. So this is one main motivation to learn features, to learn a small set of features. Another motivation could be to visualize data. How do you visualize data points which represent persons which are characterized by 1 million features? How do you plot 1 million dimensional objects in the plane? Well, you could do feature learning and learn only 2 features and use these 2 features as coordinates in a scatter plot. So you can visualize data using feature learning. You might be interested in some understanding of the data. So what are the most relevant features? And feature learning methods tell you what are the most relevant features by statistical methods. Another important application domain for feature learning is to learn features or to transform the raw data into a new set of features that do not violate privacy constraints. So for example, if this feature here contains the social ID of the person, you might throw away this feature immediately. So you might not want to use this social ID of a person. And feature learning allows to learn features that do not violate privacy, but still are informative enough to solve the prediction that we are interested in. For example, predicting the need for an ICU. Okay, so here's maybe the main slide of my whole lecture, which shows the basic idea of feature learning methods. So the basic idea is to take this raw feature vector, this long feature vector with millions of features, for example, the pixels of an image, or all the characteristics of a patient. And we apply a map in the sense of a function, just a function. However, this function is tunable, so it contains some parameters that we can tune. And this is similar to linear predictors. Linear predictors are tunable functions. So a linear predictor is a function that can be tuned. So you can change the weight vector of the linear predictor and you get a different function. And similar, we use here again a tunable function to map the raw feature vector into a shorter feature vector, a new feature vector of length d, and this d might be 2. So we might compress n features, n raw features, 1 million raw features to 2 features only, and these 2 features we can represent in a 2-dimensional scatter plot, which I will show then later how to do that. So the question is, what is a good compression matrix? So if we don't have anything else than just raw feature vectors, so we have tons of patients for which we have the healthcare records and the social media posts. So we know the feature vectors for many, many people, but we don't have any labels. So we cannot formulate the prediction error. But still, what we can do is we can try to reconstruct the raw feature vector from this compressed feature. So we use another tunable map, R, which is short for reconstruction map, which aims to reconstructing the original feature vector from the compressed feature vector, from the short feature vector. And the quality of this, or how informative this short feature vector is, can be measured by looking at the reconstruction error, or the smallest possible reconstruction error. So we tune this reconstruction map to minimize the reconstruction error, but we will hit some error floor typically. We cannot perfectly reobtain. In most cases, it's not possible to perfectly reobtain the original feature vector. So this x hat will be different from the original feature vector x. But still, we can try to minimize the reconstruction error. And this minimum reconstruction error gives us a loss function. So it's again, the idea is to have a loss function that characterizes the quality of a map. And this map here is not the predictor map, but it's a compression map. So it compresses the raw feature vector to the short feature vector C. So the idea now of feature learning is quite simple. Well, choose the tuning parameters or the weights of this map such that the minimum reconstruction error achievable from this compressed feature is minimum. And so this is again an optimization form of a learning problem. So also feature learning amounts to solving an optimization problem. Okay, so one example is, or one class of feature learning methods restricts the maps here, the compression map and the reconstruction map, to linear functions. So we want to use only linear maps because we can handle them easily. In MATLAB, you can quite efficiently compute matrices with vectors. So that's why it might be a useful choice to focus only on linear maps. So we say we want to compress the long raw feature vector x using a matrix W, which is nothing but a linear map, and results in a short vector z. So the length of the vector z is d. D is small, way smaller than the length of the original feature vector, which is n. And also the reconstruction. So we try to reconstruct the original feature vector from the compressed feature vector using, again, a linear map. And this linear map is called R, for reconstruction matrix. And then we obtain optimal feature learning by choosing these matrices to minimize the reconstruction error. And if you write down the reconstruction error, you get a nice expression involving a matrix product of R and W. And I will then show you how we can solve this minimization problem using principal component analysis. But first, I want to explain on a higher level different classes of feature learning methods. So another class of feature learning methods is obtained by using nonlinear maps. So instead of linear maps, here we allow now for nonlinear maps. And a very powerful representation of nonlinear maps are artificial neural networks. And this is then called an autoencoder. So these autoencoders are feature learning methods which use artificial neural networks, or ANNs for short, to compress the long raw feature vector into a short compressed feature vector C. And also the reconstruction must be nonlinear then, as we might suspect, because if we compress in a nonlinear way, then the best way to reconstruct the original data might also be nonlinear. So we might not do well if we only would restrict ourselves to linear reconstruction. So both the encoder map here and the reconstruction, or decoder, it's sometimes called also decoder map, are artificial neural networks. And I don't know if you have heard about artificial neural networks, but in a nutshell, these are just, representation of a function. And this representation involves weights, numbers that we can choose, that we can tune. And these weights we tune such that the reconstruction error is minimum. Okay, but we can also take into account labeled data. So far, what I explained so far, you can apply to any bunch of data points for which you have feature vectors. So you don't have any labels. But if you have also labeled data, you should make use of labeled data. So you should not try to reconstruct the feature vector, because the end goal might be to predict some label. For example, in this toy application I mentioned before, the label, what we want to predict is the probability that a person needs an ICU during the next week. So we should tune this compression map not to optimally reconstruct the feature vector, but to optimally predict the label. And this will typically result in a different compression map. But again, we can use here different types of functions. So we can use here linear functions, or we can use artificial neural networks for these tunable maps. Yeah, so this choice for this compression mapping has to balance between two conflicting goals. First, the first goal is to compress as much as possible the raw feature vector. So we would like to have a very small compressed feature vector C. So this D should be very small, ideally 1 or 2. However, if we compress a lot, then we might lose a lot of relevant information in the original feature that we need to predict reliably the label Y. So we need to keep relevant parts of the feature vector in order to be able to predict this label. And it's possible to formulate this in a very compact and elegant fashion using information theory. So this compression can be quantified by using a concept of mutual information. So this mutual information tells us how many bits as a measure of information does C carry about the original feature vector X. So we would like to make this mutual information as small as possible. On the other hand, we would like to have C still retaining a lot of information about the label Y. So we would like to have C having a lot of mutual information with Y. And we can combine these two goals in one objective function and then look at this optimization problem. And this is known as information bottleneck. And there are powerful methods to solve these optimization problems. But this you can only use, or this formulation requires that you have a probabilistic model for data. So you must assume that the data points are realization of random variables, whereas what I talked about so far doesn't assume any probability distribution of this feature vector X and the label Y. Okay. Then another variation of feature learning can be used to preserve privacy. So we could reformulate the criterion for finding a good compression map W by, first of all, we would like to be able to well predict or accurately predict a label Y. So we would like this compressed feature vector to still allow for predicting this label Y hat. On the other hand, we would like this feature vector C to not allow any accurate prediction of some private variable. So this S might be, for example, the name of the person with feature vector X. So we would like to choose a compression map, a feature learning map, that makes it impossible to predict the name or the social ID of the person. And we can formulate this easily using an optimization framework. So we just want to minimize the prediction error when predicting Y, but we want to maximize the prediction error for predicting the private variable. Okay. Yeah, as I said, these feature learning methods typically amount to optimization problems. So you want to minimize, you want to find a compression map W such that it's possible to reconstruct the original feature vector from this compressed feature vector C. And you want to minimize this minimal or optimal reconstruction error. And this amounts to an optimization problem. However, these optimization problems are typically challenging. So they need a lot of computation. This takes quite computational load to compute this.
Sorry?
Yes?
I can't imagine a problem where we can use this reconstructed X vector as well for the if we have some labels, and then I understand the problem. But for which case can we use this reconstruction?
Yes. So there might be application where you don't have labels, but you still want to compress, for example, in image compression. So this raw feature vector might be the pixels of a 1,000 by 1,000 pixel image, 1 million pixels. But still, you can compress the pixels into a short feature vector, which you can store, for example, in a JPEG file. And the goal of compression formats is exactly to compress in order to be able to reconstruct with a small error. So in audio and video compression, we are exactly interested in this reconstruction error.
Or yeah, speech recognition or something like that could be.
Yeah. So you might not, so think about a big team of data analysts and machine learning scientists, and these teams might have different problems. So each team uses different labels, but they all use the same type of data. And so it might be a good idea to first compress the raw data without using any particular labels, because you want to have a general purpose feature compression. However, if you want to design a tailor-made method, a tailor-made feature learning method for a machine learning problem where you're interested in labels, then you should, of course, not look at the reconstruction error, but at the prediction error you would get from these compressed features.
Yeah. Okay. Thank you.
You're welcome. Any other questions? Okay, so as I said, this learning the optimal compression maps typically amounts to solving complex, computationally hard optimization problems. And it turns out there are cheaper alternatives. And one such alternative is called random projections. And here you learn new features, or you construct shorter features by using as a compression map a fully random matrix. So you generate the matrix by using realizations, IID, which stands for independent and identically distributed random variables, for example, from a Gaussian distribution or from a Bernoulli distribution, and you populate, using these realizations, you populate a matrix W. And here is no learning or tuning of W involved. You just start your favorite random generator in MATLAB and generate the random matrix W. And you can use this random matrix W to learn new features, because you choose this matrix to have way less rows, D is small, than columns. And it turns out that in quite many settings, you do not lose much information. So these random projections retain most of the relevant information in many, many scenarios. And this